Hi, class. In this section, we're talking about a technique that we use sometimes to understand the behavior of a system of equations. So we've already seen, we saw back in chapter 5, earlier in chapter 5, a way to, some ways that you can solve equations, but they only applied to, uh, linear equations with constant coefficients. And so that can be somewhat limiting. So if you don't know how to solve a system, at least what you can do is try to see what's going to happen, and that can help you understand the physical situation that you're modeling. So the the systems that we're looking at, I'll write out right now. So we have two equations and two unknowns. Our unknowns are dx and dt, and they're both functions, or sorry, dx dt and dy dt. So x and y are the two quantities that we're trying to solve for, and then t is our independent variable. And so these are both first order equations, not necessarily linear or anything like that. And then the important thing to note is that there is no t in the right-hand side. And so examples that we've seen like this is like the interconnected tank. So for example, we have the interconnected tank problems. And the name that we can give to this, because there's no t in the right-hand side, these are called autonomous systems because there's no t in the right-hand side. So we can take advantage of this by plotting x and y as trajectories. So let's draw a little example of this. So let's say we have these two plots and pause it. So these two graphs, one is x of t, one is y of t. So both have t on the first axis, and then x or y on the second axis. But what we're going to do is combine them together um, onto an xy axis. So at each point, we'll have the x and y point corresponding to each time point. So at 0, right, this is 0 here, we have y is 0 and x is over here. So here's x of 0. This is the ordered pair, x of 0, y of 0. And then we get a t1, we're kind of over here, x of t1, y of t1. At t2, now x is 0 and y is up here. So x of t2, comma y of t2. And x of t3, comma y of t3. And then I didn't really name anything t4, but if we had it, we'd sort of be down there. And so as time increases, we are sort of marching along this trajectory, right? And so we even have some arrows. And the arrows are sort of where time appears on this chart. And so you'll recognize this as being sine of t and cosine of t, and then that parameterizes t being the parameter. That parameterizes a circle because every point on the circle, on like a unit circle, is sine and cosine. So you'll have seen this before. So you can see how putting these two things together kind of gives you a little bit more useful information than either one of the sine or cosine curves by itself. That it gives you a sense of the bigger picture of how sine and cosine are interacting. So let's write this out as a definition. So in the context of, I'm going to give this a name, in the context of a system of differential equations, we have a name for when we can parameterize something, and that is, of course, the phase plane. So let me write out the definition. So if you have x and y as solution to our system one, then whenever we plot x and y in an xy plane with the arrows showing the direction that t is going, one of those curves, one of those parameterized curves is called a trajectory, and the set of trajectories is the phase portrait, which are plotted in the phase plane. Okay, so the thing with when we did this trajectory of the circle here, we were able to do that because we knew exactly what x and y looked like. We started with the solutions x and y. But in our system one here, we don't necessarily have the solution because we don't know how to solve, we may not know how to solve it. So we want a way to be able to plot the phase portrait and the trajectories without explicitly knowing the solution. And so here's the trick. We want to think of y as a function of x, right? But of course, x is a function of t. So y equals y of x of t. And so what's the derivative of y with respect to t? Well, by chain rule, that equals dy dx times dx dt. Well, we know something about dy dt and about dx dt, but we don't know anything about dy dx because that's what we're trying to like kind of get at is what's the relationship between y of x? What is y as a function of x? So let's divide, and we end up with dy dx equals dy dt divided by dx dt. But from our differential equation, our system, dx dt equals f and dy dt equals g. So that's g of xy over f of xy. So that's this gives us kind of a new differential equation that I'll rewrite here. Dx equals g of xy and f of xy. And the key thing here is that because we didn't have any t's in the right-hand side of our original system, this equation here doesn't have any t's. And so this is like a new differential equation. And so this is called the related phase plane differential equation. And this is what we can use to try to plot our trajectories. Since t is missing, we'll have to sort of figure out the direction of our trajectories, but this gives us that x and y relationship. We may not be able to solve this, but we do have some techniques. We have our direction fields, which helped us get a picture of what the solutions look like. And that's exactly what we're after, is kind of just a picture. And what we're going to see is that we get a few different types of trajectories. So one is a single point. And that's where as t moves, your point doesn't move at all. So you might imagine that that would happen when your derivatives, when your dx dt and your dy dt are zero because you're not moving anywhere. But we'll get to that in a second. So that's one type of trajectory. Another one might be, as you can imagine, a non-closed arc that doesn't intersect itself. So that's kind of like so here we can draw these. This one just looks like that. It's a point. This one kind of looks like that. The next one would be a closed curve, which is what you would get if you kept graphing that sine and cosine example. You'd get a full unit circle. So that might look something like this. And that indicates that you have periodic motion, just like you have with sine and cosine. And what's nice is that the existence and uniqueness theorem gives us as long as you're as long as you satisfy the conditions of it that your f and g are continuously differentiable, that this theorem implies that trajectories don't overlap unless they're exactly the same. And that's because if you had one trajectory that went like this, and then another trajectory that went like this, and you were at this point, if you started here, uniqueness says that you can't go both directions. There's only one solution. So this doesn't happen. So the first thing we usually want to do when we are trying to sketch out a phase plane is uh, look for special points where the behavior is, you know, acting like, special. So we'll start off with this definition. If f and g, we look for points where f and g uh, are equal to 0 at the same time. And we call those critical points or equilibrium points. And the reason that this makes sense as a thing to do is because remember our system looks like this. So if f of x0 at a particular point, f of x0, y0, and g of x0, y0, x0, y0, if those both equal to 0, and then you have constant solutions, well, let's see, let's write it like this. And if you have constant solutions, x of t is equal to x naught for all t, and same with y of t is the constant solution y naught, then you get dx dt and dy, that's an equal sign, and dy dt are both equal to 0 because they're constant solutions, so the derivatives are 0. So these constant solutions are a solution, is a solution to the system. And they're kind of special because they're not changing anywhere. They're just constant. So if, you can imagine if you plotted this on the phase plane, you would just have a point at x naught, y naught. And those are going to be really special kind of points where everything stays still. So the first thing we do is look for those points and then kind of figure out what's going on near those points. And what we find is that there are different types of critical points that have different behaviors around them, and but there's kind of a finite number of them, and we can learn from a few key examples. So let's start off with an example. So here's our system, and the first thing we're going to do is find the critical points, which is really obvious here. So we just set dx dt and dy dt equals 0, and so the critical point is 0, 0, the origin. And then the phase plane equation is this. It's dy dx, and I'm just putting this divided by this, and so the negative signs cancel. So now what I want to do is draw the 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 slope fields that like we learned about back in chapter 1 for this equation. So there are different ways that you can plot these. It may be easiest for you to do this in MATLAB or something if that's something that you are familiar with. But I found a fairly kind of okay, easy to use tool on the internet, which I'll pull up now. So I don't know, this site Desmos has different, looks like different tools that just like maybe people have made, but this one seems to be okay for now, but you can do this any way you like. So what I'm going to do here is put in our phase plane equation. So 2y over x. And then you can see here you can adjust your, I want to go from like maybe -2 up to 2 because I know that I want to be around 0. And then same for y. I'm going to go from -2. This is hopefully easier for you to do, not in Tableau like this. Okay, so let's get back. Ooh, let's zoom in. And then this adjusts the number, but we can adjust the length of the lines with S and then the number of them with N here. Okay, so this is the deal. This is uh, our slope field, right? And this is what's going on around 0, 0, 0. But what we don't have on here, we don't really have our trajectories. We could kind of draw them, but we don't have the arrows because we've removed t from the phase plane equation. So we need to still kind of figure out what's going on here. So let's say that we started up, let's say we had a point here. Now our trajectory is we can see that it's going to kind of go down this way. I didn't mean to put the arrow, or it could go up this way. We haven't figured out the arrow yet. But if we're in this quadrant, x is positive, so dx dt is going to be negative because dx dt equals -x. So we're going to be moving in the negative x direction, which is left. So our arrows are going to have to go this way. And you could think about it the same way, and that's going to be true. Okay, so that's going to be true in our in this quadrant too, in the lower right, because x is still positive. So dx dt is going to have to be negative, and we're going to be moving in that direction. You could think about it the same way with y. So in the first quadrant, in the top right, y is positive, so dy dt is negative, and you'll be going down. And then over here too, y is positive, and so dy dt is negative, so we're going down. And then over here, if we have our trajectories, we're going to be going up because our y is negative and our x is negative, which means that both dx dt and dy dt are positive, so we're going up and to the right. So all these trajectories are kind of flowing right to our critical point. And we can draw all of these. We have these kind of, all these trajectories that are heading towards our critical point. And so we say that this, because we're kind of flowing into them as time goes on, we say that this critical point is asymptotically stable. Because even if you had some sort of, you know, if you're kind of going along and then something came and jerked you over here, we're still gonna like kind of keep flowing into our sort of stable position. And it's asymptotically because that's what's happening as t goes to infinity. So that's one sort of critical point that you can have. Now let's think about another example. I'm going to do this over on the side because it's similar. So now our example is dx dt equals x and dy dt equals 2y. So this is the same as what we had over here, except without negative signs. So we'll notice that our critical point is still 0, 0. And our phase plane equation is the same. Because the negative signs, there are no negative signs to cancel out, but they canceled out in the last one. Oops, I'm sorry, this was 2y. Sorry about that. So dy dx equals 2y over x. So that means that we can just kind of copy our slope field over here. It's going to be the same. Okay, so we've got our same slope field, but now let's think about our trajectories again. Now, if we start off over here in where x and y are positive, now dx and dt are positive, and so they're going to go up and to the right. So now our lines are going to kind of go like this. And all of our lines are going to go in the opposite direction, right? And this is what our sort of curves look like. They're all heading away from our critical point. There's our critical point. And so this critical point, because we're moving away, this is called unstable. So these are two types of behavior that you can see near critical points. Okay, let's see another example that's a little bit more complicated. All right, here's our system. And if you set dx dt and dy dt equal to 0, which I'll let you do on your own, we get the critical point 1, 1. And of course, our phase plane equation is just dy dt over dx dt, so that's dy dx equals 4x minus 3y minus 1 over 5x minus 3y minus 2. Now, plotting the phase plane, the direction field for this is a little bit more complicated than some of the others, and it involves some mathematics that we're not going to go into in this class. So I'm just going to post the picture here from the book. So we have our critical point 1, 1 on here. And there are these kind of like two paths that cross through 1, 1 that have arrows kind of going towards the critical point or away from it. And again, it's a little not obvious how where we find those lines. But here's another line that's not on here. Let's draw this line kind of like this. So this line is 5x minus 3y minus 2 equals 0. If you rearrange that, you see it's a line, the y-intercept is negative 2/3. And so that's where dx dt would equal 0. And everything on the right of it, you have dx dt is positive, is going to the right, and everything on the left, dx dt, we're heading in the left, the negative direction. And so we have a bunch of strange paths here. So like you said, some of the things on this line are heading straight towards the critical point, but then on this other kind of line here, we're moving away from it. And some of these were like kind of on that line, and then we like track back and loop away. So there's some really strange behavior. On the other hand, some of the behavior is really predictable. So let's take this path right here that includes that point 2, 0. So we're heading off, it looks like we're heading off towards infinity, but could it happen that we like have some of the strange behavior that we have towards our other critical point where we sort of like turn around or anything like that? And the answer is no, because we know that our dx dt is always going to be positive in this region. And so we're not going to be able to like sort of track back. If we tracked back, then that would mean that our dx dt would slow down. Like if we turned around, if we did something like, you know, going like this and then turned around like this, that means that at some point here, dx dt would have to equal 0. But that can't happen because that would be a critical point. Because also we'd have dy, we're sort of like turning around in both directions. So that was a t, d, t. And we know that that's never going to happen. And so what actually ends up being true is this theorem. So this theorem says that if you have a solution to your autonomous system, then if for any like kind of path that you might have on your phase plane, if the limits as if these sort of like kind of go to a point, if x and y like go to some point, they kind of stop and don't go off to infinity, meaning that you've got your limits x star and y star, then that means that x star, y star has to be a critical point. So if your path isn't heading, like in our example up here, we knew that we only had one critical point at 1, 1. And so that means that we know that any point that isn't heading towards 1, 1 has to be heading off to infinity. That's what this theorem tells you. And then the other thing I will say about our example up here is that our critical point 1, 1 is unstable because we have some solutions that are going towards it, but some are veering away. And so we don't have this sort of like stability that we had in our last example. And so this is called a saddle point. So the last thing I'm going to talk about from this section is just to show you some other examples of what types of behavior you can get at critical points. All right, so here are some graphs of some different types of trajectory behaviors. And so remember, this is for a system that looks like dx dt equals f of x y and dy dt equals g of xy. Okay, that's our system. So let's take the spiral for a second. So the critical point in all of these is at 0, 0. That's kind of the depiction here. So if you start at 0, 0, because that's a critical point, dx dt will equal 0 and dy dt will equal 0. So your system won't move at all. Okay, that's why it's just kind of stationary there. However, the question is, what if you start? What if your initial condition is not right at that critical point, but it's nearby? And so if sort of like if you got nudged just a little bit away from your critical point, and in this spiral example, you're not going to kind of like get sucked back in to your stationary point. You're going to fly away. Okay. And so that's why this is unstable, because if you're off by just a little bit, if there's, I don't know what's going to happen, but if you're off by just a little bit, then you don't get to go back home. You fly off. On the other hand, if you are on this node here, if you start a little bit off, then here you go, you get sucked right back in. And so that's why this one is stable, but the spiral is unstable. Now the node is asymptotically stable because you don't really get stability necessarily until like time, until like sort of as time goes on. Whereas with the center, even if you're off a little bit, you still sort of have stability in that you are constantly on this trajectory. You're not flying off to infinity. So you still you're not exactly back home, but you're still very close to home. So that's stable, not asymptotically, because you're like stable already. You're already on this like sort of stable trajectory. The spiral again is asymptotically stable because this is the opposite of this unspiral stable. If you start off a little bit, you're going to get sucked back in because the direction is going the other way. So it's going towards your home. And then let's see, we have our saddle here, which is the one we saw in the last example. Sometimes you get sucked back home, but for most of the time, if you're just off by a little bit, you're going to get sucked off to infinity. And same thing with this unstable node right here, where your lines are going away from your critical point. So if you're able to understand sort of the behavior of a system, now you can understand what's going to happen depending on what your kind of initial conditions are, and what's going to happen as time goes on. So these phase diagrams can be really important for understanding the behavior of your system in general, and that's why it's an important tool for understanding dynamical systems.